In 1965, more than 160 kilometers above Earth, astronauts looked down at the Sahara and noticed something that should have been impossible to miss. A near-perfect spiral, about 40 kilometers across, sitting in the middle of the desert on a planet we thought we'd already mapped. Picture that small spacecraft window. North Africa slides beneath you in seconds. The Sahara looks flat at first, long bands of sand, dry riverbeds, a few dark mountains. Then a pattern cuts through the monotony. Wide, pale rings, one inside another, filling an area larger than many cities. From orbit, it's obvious. From the ground, most people never knew it existed. We almost missed a 40-kilometer landmark. Welcome to the Nocturne history, where mystery and sleep walk side by side. This is Mystery History for Sleep, a slow journey through deserts that hide spirals, stories that don't quite fit the maps, and landscapes that quietly challenge what we think we know about the past. You don't have to solve anything tonight. You only have to follow the circles and let the images settle in your mind. Back then, spaceflight was still young. The Gemini missions were testing how humans could live and work in orbit before anyone tried for the moon. Astronauts acted as the eyes of geologists and geographers, taking thousands of photographs for scientists who wanted to see Earth from a new angle. The Sahara, spreading over more than 9 million square kilometers, was a natural target. Inside that huge space, this strange circle quickly became a favorite landmark, a natural bullseye they used to check where they were. NASA archived the images and passed them on to researchers. In those early photos, you can clearly see multiple rings nested one inside another. The structure sits in modern-day Mauritania, in the Western Sahara, roughly 500 kilometers from the Atlantic coast. This isn't a small hill or a local quarry. A road could loop the outer ring and still leave room for several towns within its bounds. So, if something that large is sitting in the middle of a continent, why had nobody drawn it on old maps? Why isn't this taught alongside the Grand Canyon or the Great Barrier Reef when we talk about Earth's big landmarks? From ground level, the eye of the Sahara doesn't look like an eye at all. Stand inside it and you see ridges, stony slopes, and far-off horizons, not a neat circle. The rings are so wide that no single viewpoint can take them all in. For almost all of human history, people simply couldn't get high enough above it to see the pattern. It's humbling to think that the shape was always there, but our eyes and tools weren't ready for it. For centuries, traders and nomads crossed this region by camel and on foot. They focused on wells, pastures, and safe passes through dunes. Mapmakers worked from their reports, sketching coastlines, rivers, and routes. A set of low ridges in the center of the Sahara didn't stand out. The desert wasn't hiding a secret on purpose. Our tools and our point of view just weren't ready to notice it. When detailed photos finally reached geologists, the reaction was immediate. At a glance, the feature looked a lot like a giant impact crater, round, centered, with ring-like structures around it. Some scientists proposed that a meteorite several kilometers wide might have slammed into this spot long ago, gouging out a huge depression and sending waves of broken rock across the surface. Others suggested the remains of a collapsed volcano, an ancient dome that had sagged and eroded over time. With only fresh photographs and a handful of field reports, early interpretations were bold and often conflicting. Here, small cracks in the foundation of our picture of Earth begin to show. We tend to assume that by the late 20th century, the planet's major features were all known and settled. Yet this structure, tens of kilometers wide, had only just entered serious scientific conversation. In its quiet way, it challenges accepted history, not the timeline of civilizations, but the idea that our view of the planet has been complete for very long. It reminds us how recent our so-called global vision really is. The planet still has surprises, even in an age of maps and satellites. As more work was done, the structure collected names. In research papers, it became the Richat structure. In astronaut slang and popular articles, it turned into the Eye of the Sahara or the Eye of Africa, because from orbit it really does resemble an eye set in the desert. Astronauts on the International Space Station still point their lenses at it today. Yet outside scientific circles and a few viral images, many people have never heard of it. A 40-kilometer spiral in the middle of the Sahara doesn't match the usual list of world wonders, so it's often left out by the people who decide what to highlight, set aside by researchers who focus on other, more famous sites. If you picture looking down from orbit right now, you'd see more than a simple ring. You'd notice layers of color in the rock. Browns, grays, hints of blue where minerals catch the sun. The outer rings blur into the rest of the desert, while the inner rings stand out as sharper arcs. In the quiet of your room, with your eyes open or closed, you can hold that view in your mind. Every 90 minutes or so, an astronaut circles overhead, and once again the Sahara rolls into sight with this calm, circular mark sitting in the middle of it all. Long before 1965, long before cameras and capsules, this shape was already here, slowly weathering under wind and sun. Soon, the view will change. Instead of looking down from space, we'll move closer to the rocks themselves and see how that simple circle turns into real cliffs, shallow valleys, and curved ridges underfoot. Before we ask how such a pattern formed, it helps to remember this first moment. The shock of finding a 40-kilometer spiral on a planet we thought we'd already mapped. If something this large stayed unnoticed until the space age, you can't help but wonder what else still lies in plain sight, waiting for the right point of view. If you feel yourself relaxing as you picture it, that's all right. For now, just let that image drift at the edge of your thoughts as we leave the quiet of orbit and begin to move closer to the ground. If you tried to walk a full loop around the Eye of the Sahara, you would travel more than 120 kilometers through broken rock and sand. From orbit, this place looks like a simple target shape. On the ground, it becomes a wide zone of ridges, slopes, and dry valleys that could take days to cross. You could spend days inside the eye and never realize you're walking through a single, giant shape. So let's drop down from that astronaut's window and stand at ground level. In front of you is not a smooth circle, but a low line of hills stretching toward the horizon. The air is dry, the light is sharp. The outer ring of the eye is so broad that it feels less like a wall and more like a slow change in the texture of the land. You might not even realize you are stepping onto something unusual until you look back and see how the terrain has curved around you. From ground level, the eye refuses to look like an eye at all, and that's exactly why it stayed hidden for so long. The structure is roughly 40 kilometers wide from edge to edge, but it is built from several distinct rings. Some ridges rise a few hundred meters above the surrounding plain. Others are shallow, almost like waves frozen in stone. If you walked from the outside toward the center, you would climb and descend over and over, crossing bands of rock that alternate between hard, resistant layers and softer ones that have eroded into gullies and narrow slots. From above, that pattern of alternating layers creates the clear rings we see in satellite photos. On the ground, though, each band feels like its own small landscape. One ring might be a ridge of darker, tougher rock that breaks under your feet into sharp fragments. The next could be a paler, softer layer that turns to powder in your hand. Dry channels cut into these bands, guiding rare rainfall toward the basin in the middle. The center of the eye is not a deep hole. It is a broad depression, several kilometers across, scattered with boulders and low outcrops. In some places, the difference in height between the outer rings and the interior floor can reach a few hundred meters, but the slopes are long and gradual. There is no single cliff that announces a boundary. Instead, you move across a series of subtle steps, and only later, looking at a map or a photo from above, do you see how those steps form part of a larger design. Spend a moment imagining the silence here. There are no trees to rustle, usually no running water, often no voices. Wind is the main sound, a steady push across your ears, a fine hiss as grains of sand move along the ground. In the distance, the line of a ring might break for a kilometer or two, then reappear. This is one reason this place stayed almost invisible to history. Caravans crossing this part of Mauritania cared about wells, grazing, and safe routes, not about tracing curves on a map. A trader leading 30 camels loaded with salt may have crossed one of these rings in the year 1200 or 1500 without ever guessing he was on the rim of a structure that an astronaut could see from hundreds of kilometers above. There's something humbling about knowing someone could cross an entire ring and never see the circle they were part of. Why isn't this taught when we talk about world geography? It raises a simple question. How many other large features don't fit the narrative we grow up with about the world's best-known landscapes? If we sketch the eye on paper with a diameter of about 40 kilometers and multiple rings inside, the scale becomes easier to grasp. Each ring can be several kilometers thick. The distance between the outermost visible ridge and the innermost ring might be 15 or 20 kilometers. That is a long walk in desert heat where summer temperatures can reach 45 degrees Celsius. Trying to see the structure by hiking across it would be like trying to understand a full painting by staring at it from just a few centimeters away. But walking still matters here because it reveals details that you cannot get from a satellite photo. Up close, you see fossils in some layers, signs that parts of this region were once under shallow water. You notice different colors in the rock, hints of changing conditions when each layer was laid down. You might find small, rounded pebbles in places that suggest old streams or shorelines. These bits of evidence quietly poke at our sense that the Sahara has always been dry and empty. They are small cracks in the foundation of the story we usually hear about this desert. For researchers trying to understand what shaped the eye, moving between these two viewpoints, the walking pace of the ground and the wide view from the sky has been essential. No single angle gives you the full truth. Seen only from orbit, the structure looks too clean, almost artificial. Seen only from the ground, it can be mistaken for ordinary hills. It is the combination that makes the mystery interesting, and that combination led some early investigators to wonder if they were looking at the scar of a massive impact. In time, geologists would come here with instruments, hammers, and notebooks, trying to decide whether this was the site of a long-forgotten collision from space or something even stranger. For now, it is enough just to walk the edge in your mind, to feel the rise and fall of each ring, and to know that beneath these ridges lies a story that took far longer than any human journey to unfold. If your eyes feel heavy as you picture it, you can rest them. And if a landscape this large can stay hidden in plain sight, it makes you wonder what other patterns we've been walking across without ever noticing. The rocks will still be there, waiting for us to ask how they came to be arranged in such a careful circle. In the late 1960s, some geologists looked at new satellite photos of the Sahara and seriously proposed that a meteor big enough to carve a 40-kilometer scar had slammed into northwest Africa. The Eye of the Sahara was briefly treated as one of Earth's possible great impact sites. It was a simple, dramatic story, a single blow from space leaving a perfect mark in the desert. Imagine a small group of researchers in 1966, gathered around a light table covered in black and white prints from NASA. They slide one image aside and another into place until a strange pattern fills the glass, a circular structure in Mauritania, about 40 kilometers from edge to edge, with ring after ring wrapped around a central depression. Someone points to the center and simply asks, "Crater." In that one word, the eye became part of a much bigger story about cosmic impacts and vanished catastrophes. Back then, Earth-orbiting spacecraft were still new. Before the 1960s, most geological maps were built from ground surveys and scattered aerial photographs. Space images changed that. A single pass could capture hundreds of kilometers of terrain. Features that were invisible on older maps suddenly stood out. Circular structures drew special attention, because nature doesn't often create large, nearly perfect rings without a powerful cause. So a first wave of researchers listed the Eye of the Sahara as a suspected impact structure. On paper, the idea was straightforward. If a meteor several kilometers wide had hit here, it could have released energy equal to millions of nuclear bombs, vaporizing rock and sending shock waves through the crust. Rough calculations suggested an impactor around 5 to 10 kilometers across might create a structure roughly this size. A big circle, concentric rings, a central uplifted zone. It ticked the basic boxes for a complex crater. From a desk far from the heat and dust, it behaved exactly the way a crater should. Soon the work moved from offices to the field. In the late 1960s and early 1970s, teams visited the region, driving or hiking across parts of the rings, chipping samples from outcrops and marking their positions on paper maps. Out here, the theory had to match the rocks underfoot. If the eye was truly a crater, there were certain things they expected to find: shattered, shocked minerals, glassy impact melt, and clear signs of rock that had been compressed and then rebounded by an enormous blow. Day after day in the field, they examined the layers. They saw sedimentary rocks, sandstones, limestones, and shales, tilted and exposed. They found igneous rocks cutting through older beds. They could trace some layers for many kilometers around parts of the rings, but the classic fingerprints of a giant impact were missing. In thin sections under the microscope, quartz grains looked strained by normal geological forces, not by the ultra-high pressures you see in proven craters. From space, the eye had looked like a textbook impact. Up close, it stubbornly refused to leave the right scars. This was a quiet turning point. From orbit, the eye still looked like a crater, but the ground truth said otherwise. Here is one of those small cracks in the foundation of a neat story. A simple, dramatic impact explanation that doesn't fit the physical evidence. In scientific journals, the language began to shift. The term suspected crater gave way to more cautious labels: circular structure, eroded dome, complex uplift. The mystery didn't vanish, it just changed shape. There's something both frustrating and beautiful about a place that imitates a catastrophe so well, yet turns out to be the work of slow, patient forces instead. If this was not a scar from a single catastrophic moment, then what was it? By the mid-1970s, some geologists argued that the eye was a deeply eroded structural dome in the crust. In that model, rocks that were once flat had been pushed up in a broad, gentle bulge and then worn down over tens of millions of years. Harder layers resisted erosion, standing out as ridges. Softer layers wore away, forming valleys. The result: a set of nested rings that only looks like an impact crater when you fly high above it. This slower story challenges accepted history about how big scars on Earth form. People are drawn to sudden, violent causes. A single asteroid arriving in an instant is an easier tale to tell than uplift and erosion working for 100 million years. Maybe that's why this shift in thinking is quietly dismissed by scholars outside geology or simply ignored in popular accounts. We like our disasters fast and our explanations simple. The Earth often prefers the opposite. For the geologists who walked the rings with hand lenses and notebooks, though, the slow version made more sense. They could match rock layers across different sides of the structure. They could measure dips and strikes, the angles at which layers tilt and the directions they point, and see patterns consistent with a dome that had been unwrapped by time. The eye stopped being a simple bullseye on a map and became a three-dimensional puzzle of rock types, ages, and movements. Over time, sample after sample confirmed the same picture. There were no signs of melted rock sheets, no shocked minerals spread over tens of kilometers, no buried core of impact glass. By the end of this phase, the consensus in the specialist community had shifted. Most geologists no longer treated the eye as an impact crater. They placed it instead in the category of unusual, large-scale erosional landforms, a natural masterpiece carved by uplift and weathering, not by a single collision. Outside that circle of experts, though, the old idea lingered. It still appears in older books, in outdated articles, and in documentaries that prefer a dramatic impact over a complicated geological history. So today, when you see this 40-kilometer spiral from space, you're looking at a place that once sat on lists of Earth's great craters and was later crossed off. The rocks tell a slower story than early interpreters hoped for, but not a less interesting one. If a perfect crater from orbit can turn out to be something else entirely, it's a reminder that even our strongest first impressions of the planet can be wrong. If anything, the rejection of the impact theory clears the way for a harder question. How do you raise a dome this big and then peel it back into rings we can see from orbit? As we move deeper into the timeline, we'll step away from human decades and into the realm of millions of years, where the real shaping of the eye began. If you feel your body settling as you listen, let it. The pace of the story is about to slow down to match the pace of the Earth itself. And as it does, you can let your thoughts slow with it, knowing that beneath this quiet circle in the desert, the planet has been working on its own schedule, far longer than any human memory. In 360 BCE, a philosopher in Athens described a city built in rings of land and water, with a central island and canals leading to the sea. 2,000 years later, people saw satellite photos of the Eye of the Sahara and thought, that looks familiar. A story written in Greek suddenly seemed to line up with a pattern in the desert. For some, it felt as if a myth had quietly been given a set of coordinates. The philosopher was Plato, and the story is the one we now call Atlantis. He says he heard it secondhand through an Egyptian priest speaking to the Athenian lawmaker Solon around 600 BCE. According to that priest, the events of Atlantis took place 9,000 years before Solon's time. That pushes the story back roughly 11,600 years before today. We like stories that reach across thousands of years and still seem to point at something we can see. Plato places Atlantis beyond the Pillars of Heracles, the ancient name for the narrow strait at Gibraltar. Past that strait, he writes, was an island larger than Libya and Asia together, controlling routes in and out of the Atlantic. At the center of that island, he describes a capital built as a series of concentric circles, alternating rings of sea and land around a central hill. The royal palace sat on the innermost island, linked to the outer world by bridges and a straight canal. Read this way, the dialogue starts to sound less like legend and more like a set of instructions. If you read the lines in his dialogue, Critias, closely, they almost sound like a blueprint. 3 rings of water, 2 rings of land between them, bridges connecting the rings, a circular wall on the outermost ring, a main canal said to be 100 feet deep, 600 feet wide, and many kilometers long, cut straight from the sea to the central harbor. He even gives diameters in stadia, an old Greek unit of length, turning this legend into something that feels measured instead of vague. Details like that make it tempting to believe there must be a real blueprint hidden underneath the philosophy. Now hold that text in your mind and look again at the Eye of the Sahara from space. You see a roughly circular structure about 40 kilometers wide made of nested rings. There is a central zone and bands around it. At a quick glance, it is easy to see why some people think of a city of rings described in a 2,300-year-old text. The visual echo is strong enough that it has become the thumbnail image for many videos and articles linking the eye to Atlantis. In a single glance, a geological structure becomes a candidate for the most famous lost city in Western imagination. But step back and compare the details more slowly. Plato's city is an island in the sea. The eye of the Sahara is more than 400 kilometers from the modern Atlantic coast. Plato's rings are water and human-built embankments. The eye's rings are layers of rock, tilted and exposed, with dry valleys between them. At Atlantis, boats move along canals and harbors. At the eye, there are no known remains of large docks, piers, or seawalls. The more you check detail against detail, the more the overlap begins to thin out. Even the basic setting is different. In the dialogue, Atlantis is described as a powerful naval state, sending fleets and waging war on Athens and others. Its strength comes from ships, metals, and organized agriculture. The region around the eye, by contrast, shows traces of much older rocks and a history written in geology first and only later in scattered signs of human activity. To treat the eye as Plato's city, you have to imagine a coastline and a harbor where the evidence so far does not support one. To turn the eye into that capital, you have to picture harbors, fields, and fleets, where the rocks for now stay silent. This doesn't stop people from trying, and in a way that's understandable. There is something compelling about the idea that a text from 360 BCE could correspond to a real place we can point to on a map. It challenges accepted history. We're used to thinking of Atlantis as pure allegory, a teaching story about pride and collapse. Seeing those rings in the Sahara introduces doubt. What if there was at least a kernel of geography behind it? It whispers that maybe we were a little too quick to file Atlantis under myth and move on. Most scholars argue that Plato invented Atlantis as a moral tale, not as a historical report. They point out that he uses it to compare different kinds of states, and that there are no independent sources from his time confirming such a massive empire. In academic circles, attempts to match the eye directly to Atlantis are usually quietly dismissed by scholars as modern enthusiasm, not careful method. Still, outside that world, the comparison spreads because the images are so striking. In lecture halls, the eye is more often a cautionary slide about how easily viral images can outrun careful evidence. From a narrative point of view, Plato's description and the eye line up in only a few key ways. There is the idea of concentric rings. There is the general sense of something once important that is now gone or ruined. Beyond that, the matches start to thin out. The scale in stadia that Plato gives does not cleanly match the known sizes of the eye's inner and outer rings. The presence of clear sea around the city in his story does not match a structure now stranded deep in a desert. Our minds are very good at circling the few similarities and quietly stepping over the gaps. So what do we do with this? One option is to throw the whole comparison out as a coincidence. Another is to use it as a reminder of how our minds latch onto patterns, building bridges between words and images that may not have any real connection. A third is to treat it as an open question, not about whether the eye is Atlantis, but about how old stories and modern landscapes interact in our imagination. All three choices say as much about how we think as they do about what the desert actually is. As you listen, you don't have to pick a side. You can simply notice how a few lines written in Greek 2,300 years ago can still shape the way people look at satellite photos today. You can picture the rings in rock and the rings in Plato's dialogue resting on top of each other in your mind, matching in some places and slipping in others. Somewhere between the story and the stone, there's a quiet space where imagination does its work. In the next part of our journey, we'll take this a step further and look not just at the words, but at the actual numbers people use when they try to make the desert and the dialogue line up. And if old words can change the way we look at a single spot in the Sahara, it's worth wondering what other landscapes might be waiting for a story before we really see them. For now, if your eyes are heavy, you can let them close and let those two sets of rings slowly drift together and apart in your thoughts. In some modern comparisons, the key number is not 40 kilometers, but 23. Supporters of the Atlantis theory argue that the innermost major ring of the Eye of the Sahara is roughly 23 kilometers across, and they say that number lines up with the size of Atlantis's central city if you convert Plato's ancient units correctly. A single figure becomes the hook that holds the whole comparison together. To see how they get there, we have to put the story into numbers. Plato doesn't just describe rings of land and water. He also gives measurements in stadia, an old Greek unit. One stadion is often taken as about 185 meters, although some scholars argue for slightly different values. In his dialogue, he lists the widths of the water rings and land rings, the size of the central island, and the total diameter of the circular harbor and its outer wall. It reads less like pure myth and more like someone sketching a plan, and that feeling of precision is what invites people to treat his numbers as if they could be converted straight into a map. When modern writers try to compare those values to the eye, they start by adding up the rings. Depending on exactly how you interpret Plato's text and which version of the stadion you choose, you can get a total diameter in the range of a few tens of kilometers. Some calculations land near 23 kilometers, others closer to 25 or even 30. That spread alone shows how uncertain these conversions are. A small change in the base unit quickly adds up when you multiply by dozens or hundreds of stadia. Now bring in the satellite images. If you draw a circle around the most obvious inner ring of the eye, you do not get the full 40-kilometer width of the whole structure. You get something much smaller, on the order of 20 to 25 kilometers, depending on exactly where you place your line. This is where the phrase 23 kilometers comes from. It is a mid-range figure, taken as a kind of compromise between different ways of tracing the inner ring. For those who already believe the Eye and Atlantis are connected, that coincidence feels important. For anyone watching from the outside, it's also a reminder of how easily meaning appears once you've decided what you're looking for. Seen from a distance, the match looks neat. A central feature in the desert, roughly 23 kilometers wide. A legendary city whose diameter some readers calculate as nearly the same. But when you look closer, the numbers begin to blur. Plato's text is not a modern engineering report. Plato's text is not a modern engineering report. The copying of manuscripts over centuries has introduced small variations in the figures. The value of the stadion is not fixed like a meter today. All of that creates room for averages, guesses, and choices. This is where cracks in the foundation of the neat 23-kilometer claim begin to show. Change the stadion length to another value used by classicists, and the calculated diameter of Atlantis's main rings shifts away from the eye. Treat some of Plato's numbers as rounded or symbolic, and the link becomes looser still. The more you push the math, the more you see how much depends on which assumptions you quietly accept before you begin. What first looked like a hard match starts to feel more like a range you can slide back and forth. On the ground, the numbers are also less tidy than they look in diagrams. The eye's rings are not perfect circles. They are broken, offset, and irregular in places. Measuring across one part of the structure might give you 22 kilometers for a chosen ring. Another line a bit north or south might give you 24 or 26. Geologists see this as normal for a natural landform shaped by uplift and erosion. People chasing exact matches to Plato's figures, however, tend to pick the path that best suits their target value. Most of the time it isn't deception, just a quiet preference for the measurement that feels most satisfying. There is also the question of how many rings you count. Plato clearly describes a certain number of water and land bands. At the eye, the rock layers form several prominent ridges and valleys, but how you group them depends on scale. Do you count only the major ridges you can see from space? Do you include every smaller arc of rock and every shallow depression? Different answers give you different ring counts, which can be made to fit or not fit the legend. All this doesn't mean the comparison is worthless. It simply shows that the numerical side of the argument is far from solid. In a way, it challenges accepted history and also challenges the more dramatic alternative. Traditional scholars are right to point out how slippery the conversions are. Enthusiasts for the Atlantis theory are right to say that the rough scale is at least in the same ballpark. The eye is not a tiny hill. It is tens of kilometers wide, on the order of the size Plato imagines for his capital. The trouble begins when roughly similar quietly turns into exactly the same. What is often missing in popular videos and articles is this middle view. You usually hear either the match is perfect or the match is ridiculous. The reality, down at the level of units and margins of error, doesn't fit the narrative on either extreme. That nuance is less exciting than a knockout punch. So it is easy to see why it gets quietly dismissed by scholars on one side of the debate and by storytellers on the other. We are drawn to clean victories. The numbers here offer only a carefully balanced maybe. If you are listening to this while you rest, you don't need to solve the math yourself. It is enough to know that there is a band of numbers, somewhere between 20 and 30 kilometers, where a legendary city and a real landform partly overlap in scale, but refuse to snap together exactly. The story of the Eye and Atlantis cannot be settled with a calculator alone. It lives in the space between what the figures suggest and what we want them to prove. And that leads us naturally to the next layer of comparison, the part that goes beyond diameters and unit conversions. Numbers are only one way people try to link these two places. Others point to location, climate, and stories of sudden destruction. Those are harder to pin down, but also harder to ignore. For now, you can let the figures drift to the back of your mind, knowing that the next piece of the puzzle lives not just in measurements, but in the wider world wrapped around the rings. If your eyes are heavy, you can let them close, and let that loose band of numbers stretch and soften in your thoughts, making room for the broader landscape and the old stories that surround it. The Eye of the Sahara sits more than 2,000 kilometers from the Strait of Gibraltar, yet people argue it matches a story about a seafaring empire beyond the Pillars of Heracles. That number, thousands of kilometers from the sea, should make you pause, and it hints at how far some of these parallels have to stretch. Turning a landlocked circle into the capital of an ocean empire already shows how hard the story is being pulled. Modern Atlantis videos often arrange things into lists of proofs. We'll look at 6 of the most common: the position west of the Mediterranean, the idea of a nearby sea, the story of sudden destruction, the animals, the metals, and the rise and fall of a powerful culture. Each is built on a real detail, but the way those details are stacked together often challenges accepted history. They're less like fixed facts and more like pieces that can be arranged to make different pictures. Start with location. Plato says Atlantis lay beyond the Pillars of Heracles, the ancient Greek name for Gibraltar. Beyond that, he describes a larger ocean and an island that controls the passage. The Eye, in modern Mauritania, does sit on the Atlantic side of the old Mediterranean world, in the western fringe of North Africa. On simple maps, it isn't hard to shade a big block of land and declare, "This was the island." But that move quietly turns an island into part of a continent, something most classicists see as a serious step away from the original text. It works on a slide in a video, but it's a long way from the tight language Plato uses. Then there is the water. Today, if you stand inside the Eye, you see dry basins and rock, not harbors and canals. Yet we know sea levels were lower during the last ice age and later rose by more than 100 meters as the big ice sheets melted. Around 12,000 years ago, shorelines everywhere were shifting, and the Sahara went through wetter phases when rivers and lakes dotted areas that are now dunes. People who connect the eye to Atlantis use this to argue that what is desert now might once have lain closer to the sea, or at least been surrounded by enough water to inspire tales of channels and moats. Wetter, though, is not the same as coastal, and the gap between lake country and sea empire is a wide one. Next comes destruction. Plato describes Atlantis sinking in a single day and night of earthquakes and floods. If we take his 9,000 years before Solon line literally, that would place the disaster around 11,600 years ago, close to a real climate shift at the end of the last glacial period. Some researchers also discuss a proposed comet impact around 12,800 years ago, which they say may have triggered abrupt cooling and later warming. Supporters of the eye as Atlantis idea borrow this and suggest that whatever shook climate and sea level then could be the same kind of event that erased a coastal civilization and left only inland traces. The pattern can feel neat. A legendary flood, rising seas, and a strange, ringed landform whose rocks are older than any written record. But here, cracks in the foundation appear. Geologists see no clear layer of ruins at the eye, no tsunami deposits, no city buried under a single catastrophe layer. If a flood or earthquake did wipe out a settlement here, it has not left the kind of direct evidence archaeologists usually rely on. The story of sudden loss is there in Plato, but so far it isn't written in the sediments around the eye. Other parallels focus on life and resources. In Plato's account, Atlantis has many elephants. We know North Africa did have elephants until a few thousand years ago, and fossils of large mammals appear across the Sahara. Atlantis is also rich in metals, including gold, copper, and a mysterious substance called orichalcum. The wider region around the eye contains mineral deposits, and later empires in North Africa controlled key trade routes. All of that is broadly true, but it applies to a huge area, not to one 40-kilometer structure. Turning this region once had elephants and metal into this exact ring was the capital city doesn't fit the narrative of careful historical work. It's the kind of jump that feels satisfying in a headline and fragile when you start asking for specifics. Maybe the strongest parallel is not physical at all, but cultural. Atlantis is portrayed as a great power that rises, becomes arrogant, mistreats its neighbors, and then falls. The moral lesson is simple. Even the mightiest state can collapse. When people look at the eye, isolated in the Sahara, they see a symbol that echoes that arc, a center that feels like it should have a story attached and instead sits quiet and unexplained. The lack of confirmed palaces, harbors, or city walls is quietly dismissed by scholars working outside the mainstream, who argue that time, sand, and erosion can erase even large human works. In that silence, it's easy to project any lost culture you want onto the rings. Put together these 6 kinds of parallels: location, water, destruction, animals, metals, and cultural story, form the backbone of how the eye was linked to Atlantis in modern theory building. None of them, on its own, is strong. All of them are at best suggestive. But when they're presented in a row with dramatic music, diagrams, and satellite images, they can be persuasive. They don't fit the narrative of slow, cautious scholarship. Instead, they rearrange old details into a new pattern and invite you to believe it's the only one that makes sense. If you're not watching closely, could be and must be start to sound the same. If you're still awake, notice how much depends on choices. Which dates to trust, which maps to highlight, which parts of Plato to take literally, and which to treat as metaphor. Change any of those inputs and the neat chain of parallels starts to loosen. For some people, that uncertainty is enough to walk away from the whole idea. For others, it keeps the fascination alive because a theory with gaps leaves room for imagination. One person sees the gaps as a warning sign. Another sees them as an invitation. In the background of all this, though, The land itself remains. Beneath the rings and the stories, there are real rocks with real ages and structures that don't care about legends. Geologists have walked those ridges with hammers and notebooks, and what they found points toward a very different origin for the eye, one written in pressure, heat, and erosion over immense spans of time. As our focus shifts from stories back to stone, you can let your thoughts slow down. The human theories may rise and fall like the empires they describe, but the deeper explanation has been building here grain by grain, layer by layer, for millions of years. If your eyes are heavy, you can let them close and let that slower timescale settle gently in the back of your mind. At more than 180 confirmed impact craters on Earth, scientists find the same tiny fingerprint over and over again: shocked quartz. At the eye of the Sahara, geologists went looking for that fingerprint across nearly 40 kilometers of rock, and they found none. To understand why that matters, picture what happens when a big asteroid hits. We're not talking about a small meteor that burns up in the sky, but a chunk of rock a kilometer or more across, striking at maybe 15 or 20 kilometers per second. The energy is huge. Pressures in the target rock can jump above 10 or even 30 gigapascals, and temperatures spike so fast that minerals don't have time to behave normally. Quartz, which usually forms neat, ordered crystals, gets its internal structure bent and broken in a special way. Under a microscope, it shows distinctive lines called planar deformation features. That is shocked quartz. When geologists first visited the eye in the late 1960s and 1970s, they had that picture in mind. The satellite images showed a circular structure, roughly 40 kilometers wide, with rings and a central zone. On paper, it looked like it could be a complex impact crater, similar in scale to others known around the world. So in the field, they collected samples from many parts of the rings: the outer ridges, the inner slopes, the central area. Back in the lab, those rocks were cut into thin slices, polished, and studied under polarized light. What they saw, again and again, was ordinary deformation. Quartz grains showed signs of normal geological stress, bending, minor fracturing, features you can get from tectonic forces or long burial. But the sharp, parallel lines of true shock deformation were missing. There were no patches of glassy melt spread over large areas, no thick sheets of rock that had been liquefied and then cooled. In proven impact structures, you often find mixed-up breccias, rocks packed with broken fragments fused together. At the eye, the layering was disturbed, but not in that violent way. This absence was not based on a single rock from a single trip. Over the years, multiple teams sampled the area. They mapped the structure at different scales. Some looked specifically for shatter cones, conical fractures that form under intense, outward-moving shock waves. Those are common, for example, at the 1.2-kilometer Barringer crater in Arizona and at larger sites. At Richat, they didn't turn up in a convincing pattern. Bit by bit, the checklist for an impact crater went unanswered. If you're wondering why isn't this taught when people talk about the eye and Atlantis and giant craters, you're not alone. In many popular accounts, the original "maybe it's an impact" idea is kept alive, while the follow-up field evidence is quietly dismissed by scholars outside geology or ignored altogether. A big crater sells the story more easily than a careful explanation of what's missing. For the working geologists, though, the conclusion became clearer. You simply don't get a 40-kilometer-wide impact structure without at least some of those signatures. At Chicxulub in Mexico, the 180-kilometer crater linked to the dinosaur extinction, shocked minerals and impact melt are widespread. At smaller craters, like the roughly 24-kilometer Ries crater in Germany, the same distinctive features appear. Scale up or down, the physics of high-speed impact leaves marks you can't fake with normal erosion or uplift. So if the eye wasn't carved in a single moment by an incoming rock, what did the fieldwork reveal instead? The detailed mapping showed ring-shaped outcrops of different rock types, dipping away from a central point, like layers of an onion tipped up and worn down. Intrusions of igneous rock cut through older sedimentary layers. Some units could be dated to around 100 million years ago or more, long before any human story. The pattern was far better explained by a dome of rock that had been pushed upward from below and then slowly stripped by wind and water. This is where the narrative starts to shift. The eye is no longer a frozen explosion. It is something that rose and then unraveled. That story challenges accepted history in a different way. We like sharp events with clear causes. A single asteroid at a single moment is neat. A deep, slow dome rising over millions of years, then eroding into rings, is harder to picture, but it fits the evidence in the rocks much better than a missing crater. None of this makes the place less interesting. In some ways, it makes it more so. Instead of being the leftover scar of a brief disaster, the eye becomes the exposed cross-section of a much longer process, a kind of open book showing pages from deep inside the crust. The lack of shocked quartz is not a disappointment. It is a clue that points away from the sky and back into the earth. As you let this sink in, you can almost feel the pace of the story slowing down. We're leaving the sudden impact idea behind and moving into a timescale where 1 million years is a short chapter. In the next part of this journey, we'll follow that hint from the field evidence and step back to a time more than 100 million years ago when this part of Mauritania was not a desert at all, and something hidden beneath the surface began to push upward. If your mind feels heavy with all these details, it's fine to let it rest. The rocks have been here a long time. They can wait while we ease into their story. Around 100 million years ago, the place we now call the Eye of the Sahara was not a desert at all. It was part of a region on the African continent where magma was slowly pushing upward from deep in the crust, lifting a dome of rock more than 40 kilometers across without anyone there to see it. To picture this, forget the sand for a moment. We are in the middle of the Cretaceous period. Dinosaurs still walk the earth. The Atlantic Ocean is younger and narrower than it is today, and Africa is drifting away from South America at a few centimeters per year. As the plates move, heat from below finds weak spots in the crust. In this part of what is now Mauritania, that heat finds a path upward. Geologists studying the eye have found unusual igneous rocks, including carbonatites, that can be dated to roughly 94 to 104 million years ago. Those numbers come from radiometric dating, measuring tiny traces of radioactive elements in mineral grains. The ages cluster in a range that points to a phase of magmatic activity in the mid-Cretaceous. In plain language, something hot and buoyant was rising, and it warped the overlying layers into a gentle dome. Imagine a stack of flat sedimentary rocks laid down over hundreds of millions of years. Sandstones, limestones, shales. Now imagine a blob of low-density material rising underneath them, like dough pushing up under a crust. The layers flex upward toward the center, bending but not breaking completely. At its peak, the uplift in the Richat area may have raised the central rocks by several hundred meters compared to their original level, enough to change river paths and local slopes long before erosion took hold. This kind of feature is sometimes called a structural dome. The eye is one of the largest and clearest examples on the continent. Its central zone is built from older rocks, some more than 500 million years old, brought closer to the surface by the uplift. Younger layers drape around them in rings. Later, magma forced its way along fractures, cooling into resistant dikes that today stand out as ridges. All of this happened tens of millions of years before any human existed. It's worth pausing on that timescale. Between 100 million years ago and the appearance of our own species around 300,000 years ago, there is a gap so large that mountain ranges can rise and wear down, seas can advance and retreat, and climates can swing many times. When people try to tie the eye directly to stories from 10,000 or 12,000 years ago, they are reaching across a gulf of time that doesn't fit the narrative of a single short-lived civilization. Back in the mid-Cretaceous, though, the main story here is still underground. Magma intrudes along weaknesses in the crust, cools, and crystallizes. Some of it never reaches the surface, becoming solid bodies locked inside the dome. What survives best is the overall shape, a bulge of rock with a pattern of concentric structures around it. Over millions of years, the forces that pushed the dome up slow down or stop. Without continued support from below, the uplifted region becomes vulnerable to erosion. Rain, rivers, and later wind begin to strip material away. Harder rocks resist better. Softer rocks wear down faster. This difference in resistance is what eventually carves the stair-step pattern of ridges and depressions we now see as rings. Seen in this light, the eye is not a crater left by something that fell from the sky. It is a window into the crust, opened slowly by uplift and then widened by erosion. That interpretation quietly challenges accepted history for people who grew up hearing that all big circles on Earth must be impacts. The lack of shocked quartz and impact melt fits neatly with this dome and erosion model. There are still open questions. Geologists debate the exact cause of the uplift. Was it linked to a broader hotspot in the mantle, like the ones that built the Canary Islands and other Atlantic features? Was it related to stresses from the opening ocean to the west? Different studies emphasize different factors, and in that sense there are cracks in the foundation of any single simple explanation. But on the basic points, age, uplift, erosion, the data are consistent. Only much later do the conditions that will create the Sahara itself fall into place. Continental movements, changes in ocean circulation, and shifts in Earth's orbit all play a role. By a few million years ago, this part of Africa is much drier more often. The dome, already etched by water, is now sandblasted by wind. Any soft volcanic cones or loose materials from the original uplift phase are long gone. The core structure, however, remains. When you hear people say the eye is 100 million years old, this is what they mean. They are pointing to the age of the main magmatic episode that lifted the rocks and set up the pattern. The exact date of every ridge and valley is more complicated because erosion has been working here at different rates at different times. But the key point is clear. The basic framework of the eye predates human history by a factor of hundreds. As you let that sink in, the bright spiral in the desert may start to feel less like a man-made design and more like the exposed gears inside a very old machine. In the next part of our journey, we'll move the clock forward again into the last 10,000 years when this same structure sat not under endless dunes, but in a greener Sahara where people and animals left their own lighter marks on the land. For now, if your eyes are closing, you can rest with the knowledge that the dome will still be there when we return to it, just as it has been for tens of millions of years. Around 10,000 years ago, the place we now call the Sahara held lakes, rivers, and wetlands stretching over more than 1 million square kilometers. In that wetter world, the eye of the Sahara was not an isolated spiral in a sea of sand. It sat inside a greener landscape with grasslands and scattered water bodies where today there is almost nothing but rock and dust. This period is known as the Green Sahara, or more formally, the African Humid Period. Between roughly 11,000 and 5,000 years ago, Changes in Earth's orbit shifted the summer monsoon northward. Stronger rainfall pushed deep into what is now desert, year after year. Instead of endless dunes, large parts of the interior held shallow lakes, marshes, and seasonal rivers. Some ancient basins show evidence of water tens of meters deep, spread over hundreds or even thousands of square kilometers. If you stood near the eye back then, the air would feel different. You might see patches of tall grass, scattered shrubs, and clusters of trees in low-lying areas. The ridges of the eye itself would still be mostly bare rock, but the basins between them could hold soil and vegetation after the rains. Instead of sand blowing across every surface, you would hear insects, birds, and the movement of animals coming to drink. Evidence for this Green Sahara comes from several sources. Cores drilled from old lake beds reveal layers of mud rich in pollen from grasses and aquatic plants, sandwiched between much drier, dustier layers above and below. Fossil fish bones, hippo remains, and shells of freshwater snails turn up in areas that are now more than 500 kilometers from the nearest permanent river. Even in the region around Mauritania, traces of past lakes and river channels show up in satellite images and in field surveys. This is one of those facts that quietly challenges accepted history. Many of us grow up with a mental picture of the Sahara as an eternal desert, always dry, always empty. Yet for several thousand years, from about 9,000 to 6,000 BCE, huge areas were suitable for grazing, hunting, and even early forms of herding. It doesn't fit the narrative we're used to hearing in school, so it tends to be summarized in a sentence or two if it is mentioned at all. Rock art across the wider Sahara records this different world. In caves and on cliff faces from Algeria to Niger, people painted or carved images of cattle, giraffes, antelope, crocodiles, and even swimmers. Some of these panels are more than 7,000 years old. While the eye region itself is not as famous for rock art as certain other zones, it sits within the same broad climatic system. The animals in those drawings needed grass, shrubs, and water. Their presence is indirect evidence of a landscape that could support them over long periods. Climate scientists tie the Green Sahara to subtle cycles in Earth's orbit and small shifts in solar energy. Slight changes in tilt and timing strengthen the monsoon, pushing rainfall belts north by several hundred kilometers. Over centuries, that was enough to fill basins, feed rivers, and maintain a carpet of vegetation that could stretch from the Sahel up into what is now deep desert. Later, as those cycles shifted again, the monsoon weakened. Lakes shrank, rivers became seasonal, and plants retreated to the most favorable spots. The shift back toward aridity was not instant. After about 6,000 years ago, dust layers in ocean sediments off West Africa grow thicker, a sign that more bare soil lay exposed to the wind. By perhaps 3,000 to 2,000 years ago, conditions closer to the modern Sahara were in place over most of the region. For people living through that transition, the change would have been gradual but real. A watering hole that once lasted all dry season might begin to fail earlier each year. Grasslands would thin. Herds would need to move farther between pastures. Groups who had once lived near the interior might shift their camps and paths toward more reliable zones at the edges. Some of those movements may be reflected in the spread of herding cultures and early settlements along the Nile and other major rivers. The eye's rings, carved over tens of millions of years, formed the backdrop for these shorter human stories. As the climate fluctuated, its ridges and basins would alternately host lakes, soils, or bare stone. Archaeologists have found stone tools and other traces of human presence on and around similar highland features across the Sahara, often at elevations a little above former lake levels. People seem to have favored places where they could look out over water and land with access to both. Why isn't this taught more clearly when we talk about ancient North Africa? partly because it sits in between disciplines: geology, climate science, archaeology, and history. It also adds complexity. Instead of a simple line from eternal desert to modern nations, we get a picture of lands that switched states several times over only a few thousand years. That kind of change introduces cracks in the foundation of neat timelines. As you picture the eye surrounded not by dunes, but by patches of grassland and scattered lakes, you can start to see why later legends about lost places and shifting seas are so persistent. People have been living through environmental change here for a very long time. In the next step of our journey, we'll come even closer to those people, looking at hunters, herders, and the stone tools they left near the rims of these ancient basins. For now, if you feel yourself relaxing, it's all right to let that greener Sahara settle in your mind, a quieter layer beneath the desert you think you know. Around 6000 BCE, roughly 8,000 years ago, people were camping, hunting, and herding animals along the rocky rims around the Eye of the Sahara. While we argue today about Atlantis and impact craters, the only evidence they left behind is measured in centimeters. Stone tools scattered across terraces and slopes that now look out over dry emptiness. Picture the scene during the later part of the Green Sahara. The big lakes that once covered some basins are smaller now, but they're still there in many places. Seasonal streams still run after the rains. On slightly higher ground, near the edges of these wetter areas, families set up camps. They choose spots where they can see approaching animals and other groups, where there's solid ground above any flooding, and where water and grazing are within half a day's walk. Archaeologists working in regions like this don't find ruined palaces. They find chips of flint, scrapers, blades, and points. Some are only a few centimeters long. You can hold 2 or 3 in the palm of your hand. Others are larger, shaped as axes or heavy-duty cutting tools. At sites dated to around 6000 BCE, you start to see a mix: classic hunter-gatherer tools alongside signs of early herding and more settled use of the land. The eye's geological rings would have mattered here in simple, practical ways. The harder rock ridges offered stable ground and views in several directions. The lower basins collected water and supported plants. People could move along the edges, using the high spots as lookouts and the lower areas as resources. A camp on a ridge might be only a few kilometers from a shallow lake or a dry valley that briefly turned green each year. Many of these tools are made from stone that fractures cleanly, like chert or flint. To make a blade, someone would strike a prepared core with another stone, knocking off flakes in a controlled way. Over time, that process leaves behind both the finished tools and piles of waste flakes. When archaeologists map those concentrations, they can see where people sat, worked, and repaired their gear. A scatter of tools near a former shoreline suggests repeated visits over many seasons. A denser layer might point to a longer-term camp. We also see a shift in the kinds of animals people depended on. Earlier, during the peak of the Green Sahara, big game hunting of wild cattle, antelope, and other large mammals dominated many areas. By 6000 BCE, evidence from bones and rock art across the wider region shows more scenes with herds of domesticated cattle and sometimes goats or sheep. That suggests a change from purely following wild herds to managing animals more actively. The eye's surroundings would have offered both grazing patches and natural pathways for moving herds. It's easy to forget this human chapter when we look at satellite images today. Why isn't this taught more often when we talk about early Africa? The focus usually jumps from big river civilizations like Egypt along the Nile straight to later empires along the coasts. The interior stories of mobile herders and small camps on rocky hills quietly fade into the background. They don't fit the narrative of grand monuments and monumental ruins, but they mattered to the people living there. Dating these activities is not as simple as reading a number off a dial. Researchers combined several clues: the style of tools, the depth and layering of soil, sometimes radiocarbon dates from charcoal or bones found in the same strata. Often they get ranges like 6500 to 5500 BCE rather than a single year. Even with that uncertainty, patterns emerge. Between about 7000 and 5000 BCE, there is a clear pulse of human activity across many parts of the Central Sahara, including higher ground around structures like the Eye. At night, around those camps, there would have been firelight, animal sounds, and the low murmur of voices. Children would have grown up knowing certain ridges and waterholes as part of their mental map, moving between them as seasons changed. For them, the rings were not a mystery from space or a lost city. They were landmarks, a familiar hill, a path, a place where someone once knapped a good blade. Over the following millennia, as the climate continued to dry, these ways of life became harder to sustain in the interior. Groups moved toward more reliable water sources, big rivers, coastal zones, and oases that could still hold on to groundwater. The old camps near now-vanished lakes were left behind. The stone tools stayed where they fell, wind and time covered some. Others still lie on the surface, waiting for someone to notice them. When modern visitors and researchers reach the Eye, they often focus on the big questions: impact or uplift, Atlantis or erosion. But scattered underfoot are these much smaller clues that challenge accepted history in a quieter way. They remind us that long before myths of lost empires or debates about craters, real people lived and worked here, adapting to a changing landscape thousands of years at a time. If you imagine one of those stone tools sitting on a ridge today, under a sky full of stars, you can feel how thin the line is between our world and theirs. The same rock rings rise around it, the same basic shapes in the land guide, the eye, and the feet. In the next step of our journey, we'll move forward again into the time when long-distance trade routes began to cross this region, when camel caravans and, much later, surveyors and pilots and satellites would bring the Eye back into wider human awareness. For now, if you're resting as you listen, you can let that image of a simple flint blade on a quiet slope stay with you, a small human marker on the rim of a very old circle. In 2004, anyone with a home computer and a basic internet connection could suddenly zoom in from space onto a strange spiral in Mauritania that most school atlases didn't even show. With a few clicks in early virtual globe software, the Eye of the Sahara jumped from a quiet geological term in specialist papers into the everyday screens of people who were just exploring the world for fun. For most of history, though, this place was known at walking speed. Camel caravans crossed this part of West Africa for centuries, carrying salt, gold, and other goods along routes that could run more than 1,000 km, might include 50, 100, or even 300 animals. To the traders guiding them, low ridges on the horizon were useful markers, but the idea that these ridges formed a 40-kilometer circle simply wasn't part of their world. They saw segments, not patterns. By the late 1800s and early 1900s, outside attention changed shape. European colonial powers were pushing deeper into the interior of Mauritania and its neighbors. Surveyors and officers traveled where caravans had walked for generations. They measured altitudes, sketched maps, and sometimes noted unusual rock formations. A circular area near Richat entered technical reports, but those notes stayed buried in archives and specialist journals, quietly dismissed by scholars who had bigger political and economic concerns to write about. The real shift came with flight. In the 1930s and 1940s, pilots flying mail and reconnaissance routes over the Sahara began to see the ground in a new way. From a few thousand meters up, Curves in the landscape that make no sense on the ground suddenly become obvious. A pilot might mark a ring-like structure on a chart as a checkpoint on a long, featureless leg between distant towns. After the 1960s, satellites and astronaut photographs pulled the eye firmly into scientific view. Space agencies collected thousands of images of Earth's surface, and the strange bullseye in Mauritania stood out at a glance. In technical literature, it became the Richat structure, a textbook example of a deeply eroded geological dome. Researchers measured its diameter at around 40 kilometers and traced multiple concentric units in the rocks. Papers and diagrams tried to explain how a dome could rise and unwind into rings. But outside geology, almost no one heard about it. Why isn't this taught when we list Earth's great landforms? Students learn about the Grand Canyon, Mount Everest, and the East African Rift, but not about a 40-kilometer spiral in the Sahara that astronauts use as a landmark. It doesn't fit the narrative of familiar, tourist-ready wonders, and so for a while it stayed in the background. That started to change in the late 20th century when satellite imagery trickled into public view. In the 1980s and 1990s, declassified images and commercial Earth-observing satellites produced clearer pictures of deserts, mountains, and coasts. Magazines sometimes printed striking views of the Sahara, including the eye, as curiosities with captions like "Strange circular structure in Mauritania." Still, you needed access to specialized collections, libraries, or subscriptions to see them. The real breakthrough came with the virtual globes. In the early 2000s, tools like Keyhole and then Google Earth put stitched-together satellite images onto home computers. Suddenly, a teenager in 2004 or 2005 could spin the planet, zoom down over Northwest Africa, and discover the same pattern that once surprised astronauts. This democratized the shock that scientists had felt decades earlier. As more people stumbled across the eye online, forums and early blogs began to feature it. Someone would post a screenshot and ask, "What is this?" Replies would range from impact crater to geological dome to ancient city. It challenges accepted history in a subtle way when a feature this large can be completely new to the average person, even in an age of maps and satellites. It made some viewers quietly question what else might be hiding in plain sight. At the same time, documentaries and books about mysteries of the ancient world started using satellite images as visual hooks. A neat spiral in the Sahara is hard to resist, even when the narration clearly said, "This is a natural formation." The image still planted a seed. By the early 2000s, the eye had become a minor character in a growing number of shows and articles about odd places on Earth, even if it appeared on screen for a few seconds. Around these images, modern theories began to cluster. Some writers emphasized the geological story and the roughly 100 million-year timescale of uplift and erosion. Others leaned into impact hypotheses, even after field evidence pushed against them. Still others linked the spiral to older stories like Atlantis, building long chains of argument from a mix of satellite views, ancient texts, and imagination. The same picture could be made to support very different narratives, from camel caravans counting days between wells, to pilots marking a ring on their paper charts, to millions of people dragging a mouse to zoom in from their bedrooms. The eye has moved through layers of human awareness. For most of its 100 million-year existence, no one saw the whole pattern. In just the last few decades, it has gone from almost unknown to instantly recognizable among people who share a certain kind of curiosity about maps and mysteries. If you're listening to this while you rest, you've already done in your mind what explorers, pilots, and software engineers spent a century setting up. You've traveled from the ground to the sky and back again, getting to know this circle from different heights. In our final step, we'll pull those viewpoints together, The deep geology, the human stories, and the legends that grew up around a set of rings in the sand, and ask why the eye of the Sahara still feels like an unanswered question. For now, you can let that thought sit quietly, like a distant landmark you know is there even with your eyes closed. Every 90 minutes, the International Space Station circles the Earth, and on each pass over northwest Africa, a 40-kilometer ring in the Sahara sits right there in view. Astronauts can spot the eye of the Sahara from more than 400 kilometers up, yet most people on the ground have never even heard its name. By now, you've seen this place from almost every angle. From space, it's a clean spiral. On the ground, it breaks into ridges and dry basins. In deep time, it's a dome pushed up by magma around 100 million years ago. In the last 10,000 years, it's been surrounded by lakes, grasslands, herds, hunters, and then, slowly, by sand. And in the last few decades, it's been pulled into arguments about impact craters, lost cities, and strange coincidences in old texts. So why does this one feature keep pulling people back? Part of the answer is simple. The eye doesn't fit neatly into any one story. It looks like a crater, but it isn't. Its rings look like a planned design, but they're natural. It sits in a desert we think of as eternal, yet we know that same desert was green just a few thousand years ago. All of those small contradictions act like little cracks in the foundation of the tidy picture we're used to. On the scientific side, the main framework is solid. Fieldwork shows no shocked quartz, no widespread impact melt, none of the things you'd expect from a 40-kilometer impact structure. The rock ages point to uplift and erosion, not a sudden explosion. The dome and erosion model explains the layers, the ring pattern, and the exposed older rocks in the center. For geologists, that's enough to move the eye off the list of candidate craters and into the category of unusual but understandable landforms. But science rarely closes every door. There are still details to refine. The exact cause of the uplift, how it ties into regional tectonics, how erosion rates changed as climate shifted. Those open questions are normal in geology, yet to someone looking from the outside, they can feel like gaps that invite more dramatic explanations. When you add in the fact that this feature is roughly the same order of scale as Plato's ringed city, and that the Sahara really did go through big climate swings around 10,000 to 5,000 years ago, you get a landscape that almost seems to ask for extra stories. On the human side, the eye sits at the crossroads of very different timelines. There is the 100 million year story of the rocks. There is the 10,000-year story of the Green Sahara, when lakes and wetlands supported hippos, fish, and early herders. There is the 8,000-year story of people using the high ground as camps and lookout points, leaving behind stone tools only a few centimeters long. And there is the 60-year story of satellites and space agencies turning this remote structure into a sharp image on a screen. Then, layered over all of that, is the 2,300-year story of Atlantis as told by Plato. Most historians see it as a moral tale, not a map. Most geologists see no sign of a drowned harbor city hidden in the eye's rings. Yet the visual similarity between rings of land and water in a dialogue from 360 BCE and a ringed pattern in the Sahara is hard for people to shake. It doesn't matter that the match falls apart under close inspection. The first impression is powerful. That tension between first impression and careful evidence is really at the heart of why this mystery refuses to close. Images of the eye travel quickly now. A cropped satellite shot can be shared to millions of people in a few days. A long, detailed geological paper with maps and thin-section photos might reach a few hundred specialists. One of those forms of knowledge fits the narrative of our fast visual internet culture. The other is quietly dismissed by scholars outside the field or simply never read by the wider public. There's also something about circles themselves. We're drawn to symmetry. A 40-kilometer ring in the middle of a continent feels too deliberate, even when we know erosion can carve repeated shapes. Our brains like causes that are big and simple. An impact from space, a lost civilization, a one-night disaster that sinks a city. The real cause here, slow uplift, mixed rock types, varying resistance to weathering over millions of years, doesn't land as easily in a short clip, even though it's based on direct measurements and dated samples. So we end up with two parallel versions of the eye. In one, it is a natural masterpiece, built grain by grain and storm by storm, a clear example of how deep time and simple processes can create something that looks almost designed. In the other, it is a question mark pinned to a board crowded with other mysteries. Younger Dryas impacts, disappearing cultures, old maps, and legends of islands that rise and fall. Neither version is completely wrong in terms of emotional impact, but only one is grounded in what the rocks themselves are actually saying. As you lie here listening, you don't have to pick one forever. You can let both sit side by side in your mind for a while. The geologists walking the ridges with notebooks, and the astronauts snapping photos from 400 kilometers up. The herders 8,000 years ago watching their cattle near a shrinking lake, and the person at a laptop in 2004 zooming in on a strange shape in Google Earth for the first time. Maybe the real eye here isn't in the desert at all, but in the way we look at it. The same 40-kilometer circle has carried different meanings for different people over time. For traders, it was a set of hills you passed on the way to somewhere else. For scientists, it became a test of how carefully we can read the planet's surface. For storytellers, it's a stage on which ideas about craters and lost cities play out. What doesn't change is the structure itself. The rings have been weathering for tens of millions of years and will keep doing so long after our current arguments fade. Wind will keep moving sand through the gaps. Occasional storms will still run water through the dry channels. Every 90 minutes, the eye will slip under another orbiting spacecraft, waiting to be noticed by someone looking out a window or scrolling on a screen. If your eyes are heavy now, that's all right. You can let the details blur a little, keep just the simple picture of a circle in the desert, and know that beneath the myths and debates there is a real place with real rocks that still hasn't told us everything. And somewhere, beyond this story, other patterns on the planet are waiting to be seen for the first time.